Large-scale deployment of unmanned aircraft, or drones, will transform the way we live and work. Drones can be used for package delivery, security patrol, and traffic monitoring, and they will eventually become an integral part of the smart city infrastructure. Due to hardware limitations, small multi-copter drones are unable to conduct pre-flight physical checks on their own. Pre-flight safety checks involve detecting various anomalies such as imbalanced payload, damaged propellers, malfunctioning motors, and poorly calibrated compass. Human efforts are currently required for performing such tasks, which impedes large-scale deployment of drones and increases the operational costs. To fill this gap, we present a smart landing platform that handles pre-flight checks automatically for small multi-copter drones. We designed a digital scale equipped with multiple load measuring tips beneath a flat and rigid platform surface with grid holes. The platform is able to measure the weight and weight distribution of any drone that lands on it. When a motor spins at a given output level, the propeller, if in good condition, is expected to generate a calculable amount of upward lift, which would lead to a reduction and a redistribution of the drone's weight as measured by the platform. By analyzing the instantaneous weight measurements within the statistical inference framework, anomalies in weight distribution and in actuation and propelling system can be detected if properly attributed. We propose a nonlinear least squares model with the airframe geometry constraints to analyze the measurement data and draw accurate inferences. Since the load cells are able to take instantaneous measurements quickly, a large amount of samples may be recorded in a short amount of time. As the sample size increases, it becomes increasingly difficult for a numeric solver to find the global optimal solution within a practical diagnosis timeframe. To overcome this difficulty, we derived the closed-form analytical solution to the nonlinear optimization problem and solve the uniqueness of the solution. As a result, the computing time is reduced from many minutes to a few seconds. The effectiveness and practical value of the proposed platform and algorithms are validated via extensive sets of experiments. The proposed apparatus and the diagnostic model can be integrated with other innovations aimed at increasing the level of automation in drone-enabled systems.